We're going to jump right into OLS. Start by looking at some pictures. I got two graphs of some different variables here, and let's not focus exactly what's on each axis, but just concentrate on how those graphs are presenting the data. On the left side, we can see this data pretty well shaped. There seems like a tight correlation. If we drew a line, there'd be a positive slope there. In contrast, the graph on the right side just looks kind of random. These are two very different sets of data. We want to find a way to say how well a simple line can represent a whole collection of data points. A line can be a way to summarize the whole collection of dots in a much more efficient way. I want to find a line that's close to each value of y. Now, close to is typically defined as minimizing the average squared distance, the vertical distance. But that's why it's called least squares. That's the LS part of OLS. The ordinary, common, the one we come back to again and again and again, that's the O in OLS. There's a formula for least squares. We'll circle back to that later. But first ask, well, why is this useful? It's a very powerful simplification. If I say y is some value, beta naught, plus beta 1 times x plus epsilon, then if that epsilon is small, then I'm taking that whole collection of data, all that dots, all that stuff going on in that picture, reducing it down to just beta naught and beta 1, just two values. So it's a significant compression of how much data I need to keep track of. Beta 1, the slope, can be greater than or less than 0. If beta 1 is less than 0, then the slope is negative, and there's a negative relationship between x and y. If beta 1 is greater than 0, then the slope is positive, and there's a positive relationship between x and y. If beta 1 is 0, then there's no relationship between x and y. Now, a negative relationship is not the same as a zero relationship. An example I sometimes like to use is remember when we were rebellious teenagers doing exactly the opposite of whatever our parents told us to do. We might not have quite realized it, but we were not showing independence. If when somebody tells you to do one thing, you always do exactly the other, then you're not independent. You're still completely determined by some other person. Only if there's a zero relationship are you independent. Sometimes you do, sometimes you don't. That's a zero relationship. So estimating a beta 1 equal to 0 would be a case where there's no relationship, such as the graph that I show here on this slide. Now in finance and sometimes other situations, you might see a somewhat different notation. Instead of writing beta naught plus beta 1 times x, you could see it written as alpha plus beta times x. If you've heard expressions in finance like chasing alpha or looking for a low beta, then that's from that representation of a linear regression model, where x is the market return and y is the return on a particular portfolio or one stock or something. If it's an index fund, then alpha is going to be hopefully close to 0 and beta close to 1 to replicate the market. On the other hand, if you have a completely risk-free portfolio, then beta is 0. Market goes up, market goes down, you still get the exact same alpha return. But this is not a finance class, so we'll go back to the more general case. Given some value of x, the predicted y value is going to be the average values of the y conditional on that x. All right, so here are those same two pictures now with the regression lines drawn through them. You can see there's a positive relationship in one case, while the other case is pretty much zero relationship. But how can I tell the difference? There are lots of possible criteria. One could just be aesthetic judgment, which I don't want to throw out as a completely straw man because that's not entirely irrelevant. There are cases where sort of shading into the next consideration, is it persuasive? If it looks lovely, then perhaps it can be good at persuading somebody. Can also ask, is it useful? That's sometimes a slightly different rationale than being persuasive. Can ask, is it precise? That's equivalent to asking how big is epsilon relative to the other terms. That's a bit easier to measure and formalize. But it's useful to keep in mind that these are each going to be distinct questions. We're going to have a lot of measures to say how precise is this, but that doesn't necessarily provide any judgment about is it persuasive or is it useful. One of the questions we'll, as usual, be asking is, how can we guard against being fooled? Against thinking maybe there's a relationship, maybe it looks like the dots are kind of wiggling together in some way, but they're not actually. Maybe I'm just being fooled. People draw constellations in the night sky. Sometimes it looks like the stars just line up in a row, and we humans draw a line through there. Ancient people thought that some gods put that line as stars there to communicate something to us mortals. But the apparent locations of the stars are entirely random. So how do we guard against being fooled? Against seeing lines that aren't really there? That's what I've been calling is need to think like a statistician. We ask, what if the slope were truly zero? What would I see in that case? Versus what would be a surprise if there were no relationship? What would surprise me? Oh, I thought it was zero, but it's kind of weird to see a line there. Let's go through a little experiment. Here we have y equals 10 plus 2x plus e, the error, but the error is really large. That's the plot there. You could put a line through those dots. Reasonable people could argue about what kind of line that would look like, but the line that minimizes the squared vertical distance has a slope of 1.61813. Okay, how do I guard against being fooled? What if actually there was zero correlation? What if the true value of beta 1 were 0? I could still randomly get some y values that might produce a slope that's not 0. I estimate a slope on those genuinely uncorrelated values. Well, I do that 10,000 times just to see what kind of results I get. The histogram there shows the estimated values of beta 1 from 10,000 simulations. We see the most common result is near 0. A tiny fraction of the 10,000 give values as low as -3 or as high as +3. I can see my original estimate of 1.61813 is, a bit of a distance away from 0. Only 659 out of 10,000 gave a slope estimate that was that big or even bigger. That'd be a p-value of 6.59%, which is not greater than 5%. We would not reject the null hypothesis at a 5% level of significance. So hopefully some part of your brain is now firing neurons. Oh, hey, that looks really a lot like the dice example. Yeah, it should. That was what we'd done before. Under a pretty general set of conditions, the OLS slope coefficient has a normal distribution. So the estimate of beta divided by the standard error of beta is going to have a standard normal distribution. We often call that the t-stat or the t-statistic. Because if n is small, then it's a t-distribution, but in most cases that we're going to be working on, we'll have a lot of observations and it'll have a standard normal distribution. But it's still called a t-stat. To test against the null hypothesis of 0, which is the most common, we'd form the test statistic beta hat minus 0 divided by the standard error of beta. If we want to test against some other value not 0, then we put that in. But it's very common, in fact, normal. Sorry, bad joke. Sorry. It's really common to test against 0 because that's the sign of no relationship. If there were nothing going on between x and y, no correlation, no relationship at all, then I'd expect to see a value near 0. Thus, most computer programs automatically calculate a p-value against the null hypothesis of 0. I explained this earlier. We can talk about the estimates, we can talk about the p-value, we can talk about the confidence interval. Any of those things have the same ultimate relationship and making the exact same statistical test. They're just different ways of saying the same thing. It's super easy to calculate t-stats and p-values, so most computer programs will just spit them out automatically. Now for univariate regression, just one x variable, then statistical significance for the slope coefficient is the same as statistical significance for the overall regression. Next, we're going to add in more x variables and that result will drop away. But get these easy interpretations, there's actually some cost. The cost for the nice easy result is we have to make some assumptions. The biggest hugest, most critical assumption is the first one, that X completely specifies the causes of Y. There's nothing omitted, nothing else going on. Y is determined by X and some completely random error, nothing else there. It's a really strong assumption. It's a big deal. One of the reasons we'll often add more X variables is because of that. Now we also have to worry, might there be some reverse causation? Is there a reason to think that Y is going to cause X? We also assume that X causes Y in a linear manner, which is why we're drawing a line. A line is linear. We also assume the errors are normally distributed, which is especially crucial for cases where we have small degrees of freedom, not many observations. If we have more, then we can get away with a little looser restrictions. Then we assume the error in the X variables have fourth moments defined. That's pretty typically true, although sometimes in finance you might worry about that sort of thing. Next, at least at the beginning, we assume the errors have the same standard deviation, which is what we call homoscedasticity, or that the errors are not heteroscedastic. There's no heteroscedasticity. Yeah, those are big words. They're good for impressing outsiders. Finally, we assume the errors are going to be all independent of each other. I might imagine cases, particularly in time series, where a miss in one direction means you might expect to see a miss in the opposite direction next. But with all those assumptions, then we can say the OLS estimators are unbiased and consistent. In fact, they are BLUE, the best linear unbiased estimates. Which sounds impressive, except it's best among a pretty small category of linear unbiased estimates. It's kind of like saying somebody is the best looking economist. It's not really making as big a statement as you might hope. All right, let's do some formulas. You don't really need to know them, of course, once the computer takes care of all that, but we'll talk a bit about how the formulas are derived. We have a simple problem set up as y1, yi, where that's a whole list of y values from 1 to n. That's equal to beta naught plus beta 1 times x plus some epsilon. The y and the x are known, and we're going to choose beta naught and beta 1 to minimize the error. So from calculus, you know exactly how do I minimize anything. I take the derivative and set it to 0. That's easy. And that's one of the big reasons we have squared errors here, because taking the derivative of a squared term is pretty easy. If we wanted to minimize like the absolute value of the errors, you could, except taking the derivative of the absolute value is a pain in the ass, right around 0 especially, which is kind of what I want the errors to be. It can be done, but historically that would have taken more computing power. Least squares have been around for centuries because people could do it without computers. With some calculus, I want to minimize the squared error values, choosing values of beta. There are a bunch of steps, but it's not conceptually difficult. You find beta 1 is going to be the sum of xi minus x bar times yi minus y bar divided by the sum of x minus x bar squared. The key thing to note in that formula is the top of it looks very similar to the formula for covariance. And the whole formula looks like the formula for correlation, except not quite. The correlation would have an additional y minus y bar squared on the bottom. The formula is the covariance divided by the variance of just x. And so one reason we might have trouble getting a good estimate of beta 1 is if the variance of x is really small, right? Because then we'd be dividing by a number that's really close to 0, which is obviously bad. Now, to some extent, the intercept term is almost a nuisance parameter. It's just calculated to make the rest of the regression work. It doesn't necessarily have too much meaning in and of itself. It makes the average error equal to 0. The beta 1 hat term is the slope, dy dx, delta y delta x, all that stuff you learned back in algebra class when you were an infant. You get predicted values of y by putting in the estimated value of the coefficient, multiplying that for each x value. It's all enormously useful. It's ordinary least squares, OLS, because it is just so ordinarily done. So useful as a first step, although not often the last step. In this class, we'll talk more about the next steps.